In this video, we're going to cover drug excretion as well as the important concept and parameter of clearance. We'll examine the processes involved in drug excretion and the mechanisms that can alter it. But before we define what excretion is, let's first look at this overview diagram. If you've seen the Introduction to Pharmacokinetics lecture, we went through an overview of the four important processes, A, D, and E. Drug absorption is the process by which a drug enters the bloodstream from its site of administration. Once the drug enters the bloodstream, the body distributes it to its target tissues. And now we will see how the body eliminates the drug over time and through various sites. Once the drug enters the body, the process of elimination begins. Elimination involves metabolism and excretion. When we talk about elimination, we're talking about both of these processes, metabolism and excretion. The body uses enzymes primarily secreted by the liver to perform the biotransformation of a drug during metabolism. In the drug metabolism lecture, we talked about how people can secrete more or less of the specific enzymes, which will influence how each individual metabolizes drugs. Now, excretion is the other process of elimination. So let's subtract complexity and break down what excretion is and why it's important in pharmacokinetics. Drug excretion is the removal of drugs or their metabolites from the body, from the plasma. This process is important for maintaining drug levels within a therapeutic range and preventing accumulation to toxic levels. Now, why is drug excretion so important in pharmacokinetics? In the Introduction to Pharmacokinetics lecture, we said that PK is what the body does to the drug. Learning about drug excretion helps us understand how drugs leave the body, which is important for determining dosing regimens, predicting drug interactions, and assessing drug toxicity. Okay. Now, excretion can occur through various routes, including renal excretion via urine, biliary excretion via bile, pulmonary excretion via the lungs, and other routes including sweat and saliva. Excretion focuses on the physical removal of substances from the body. In this lecture, we're going to focus on renal excretion and biliary excretion. Let's start with renal excretion of drugs and metabolites. When we talk about renal excretion, we mean the kidneys. The kidneys are the main players in drug excretion. They filter the blood to remove waste products and regulate the electrolyte balance. In terms of drug excretion, the kidneys primarily eliminate drugs through urine, and there are three processes involved: glomerular filtration, tubular reabsorption, and tubular secretion. Before we break down these processes, let's first do a quick revision of the anatomy of the kidneys. The kidneys are two bean-shaped organs that are composed of nephrons, which are the functional units responsible for urine formation. Each nephron consists of a renal corpuscle and a renal tubule. The renal corpuscle, which includes the glomerulus, this bowl of capillaries, and Bowman's capsule, is where filtration takes place, whereas the renal tubule is involved in reabsorption and secretion processes. So what happens is blood flows into the glomerulus through the afferent arteriole. Think afferent, blood has arrived at the glomerulus, and it exits through the efferent arteriole. Efferent equals exits. Blood leaves the glomerulus through the afferent arterioles. And with the renal tubules, we have the proximal convoluted tubule, which is this part here that connects with Bowman's capsule, the loop of Henle. Now, the loop of Henle is short for cortical nephrons, whereas for juxtamedullary nephrons, the loop of Henle goes all the way down to the renal medulla. Then comes the distal convoluted tubule, and finally, collecting duct. Looking at this overview process, the first step in renal drug excretion is glomerular filtration. The glomerulus is the filtering structure through which plasma passes, forming the filtrate, and then this filtrate leaves the corpuscle and passes through the rest of the nephron where reabsorption and secretion occurs. We're going to discuss the reasons behind the reabsorption process as well as why it actually occurs, okay? But then we have tubular secretion, which is the direct transfer of substances from the bloodstream into the kidney tubules by specific carriers. Now, At the end of these three processes, the drugs or substances that are trapped in the tubules will end up in urine and be excreted that way. That's the overview process. Let's have a closer look at the process of glomerular filtration. The glomerular capillaries filter blood into Bowman's capsule, which forms the primary urine filtrate. Small drug molecules will pass through the filtration structure into the tubule and, if not reabsorbed, end up in urine. This filtrate also contains water, small ions, and electrolytes, whereas larger molecules such as proteins are not filtered. Most drugs are small molecules that easily cross the barrier, and again, if they're not reabsorbed, will directly go into the urine. And in earlier lectures, we discussed how drugs can attach to proteins in the blood, a process known as protein binding. This attachment can make it harder for small drugs to pass through the filtration process. For instance, warfarin has a strong affinity for plasma albumin. It sticks tightly to albumin. Warfarin is approximately 98% bound to that protein, so during glomerular filtration, it's likely that warfarin won't be flushed out because most of it is bound to plasma albumin, which again isn't filtered. Only the unattached or free drug is filtered, okay? Another thing to note is that the kidney's filtration system comprises three negatively charged components, okay, right here. So even if a substance is small enough to pass through these barriers, if it also carries a negative charge, the barrier will block it and prevent its passage. Beautiful. So the filtrate is normally free of plasma proteins. However, occasionally proteins like albumin may slip through and become trapped in the glomerular basement membrane here. So what the body does to maintain the purity of the filtrate, we have mesangial cells in the kidney that remove any trapped molecules or residues from the mesangial space. So this process ensures that the filtrate remains free of plasma proteins. That's glomerular filtration. So we have the first step down. The second process that occurs in the kidneys is known as reabsorption from the kidney's tubules. So this refers to the movement of substances from the renal tubules back into the bloodstream, including drugs and their metabolites. So we're going from the renal tubules back into the bloodstream. If we take a closer look at this, what we're doing is we're moving solutes and water out of the filtrate and back into your bloodstream. This process primarily occurs in the proximal tubules, but it can also take place in the distal tubules and collecting ducts to a lesser extent. Now remember, glomerular filtration filters small molecules, including water, ions, and electrolytes. Because we don't want to lose all the water from the body, reabsorption occurs. So that's why reabsorption happens. The body will reabsorb 99% of the water that passes through this filtration, with only 1% ending up in urine. Okay? And there are two main pathways involved in tubular reabsorption: passive diffusion and active transport. Now, many drugs are lipid soluble, and so they can passively diffuse across the tubular epithelium, which is basically a lipid membrane, right? So these lipid soluble drugs can move from the tubular lumen, where they are initially filtered, to the interstitial fluid and then into the bloodstream. Now, what do we know about lipid membranes? That means that lipid-soluble drugs will be highly reabsorbed because they're able to pass through this barrier. But polar drugs, which are water-soluble, will not be reabsorbed and they will remain in the tubules and get concentrated in urine. And right here, we can make a connection with metabolism, my favorite subject. In the previous lecture, if you've seen it, great. If you haven't, what are you doing? We said that the purpose of metabolism is to make the drugs more water soluble and to make excretion easier through the kidneys. And now we know why. It's because water soluble drugs will not be reabsorbed from the tubules, so they will remain in the urine and be trapped. Okay. Now, there are also some drugs that undergo active transport from the tubular lumen into the peritubular capillaries against their concentration gradient. This process requires ATP energy and involves carrier proteins located on the tubular membranes. Okay? We also discussed previously how some drugs, because they are already water-soluble, they are excreted unchanged. For example, furosemide is excreted mainly unchanged in urine. This is because they are very water soluble and are not reabsorbed. So the body doesn't need to metabolize them to have an efficient excretion of these drugs. So what happens is these drugs are primarily eliminated by the kidneys because only a small portion is metabolized. This means that for individuals with impaired renal function, such as the elderly or those with kidney disease, you have to be very careful with the dosing of these drugs because it is the main path of elimination. Okay, the body won't effectively eliminate the drugs if kidney function is very low or if there is renal failure. That's reabsorption. The second step, let's move on to the third and most important process in renal elimination, which is the secretion of drugs into the tubules. This active secretion involves carrier molecules that transport the drug and its metabolites into the renal tubules. So we're going the opposite direction. We're going from the bloodstream into the renal tubules. The glomerulus filters about 20% of the blood passing through the kidneys, but specialized carriers receive over 80% of the drugs. That means that a lot of drugs are actually secreted directly into the tubules. Unlike glomerular filtration, carrier-mediated transport can achieve very high clearance, making it an exceptionally effective process for drug excretion. This direct transport of drugs into the tubules is especially important for drugs that bind to plasma proteins, because if you remember in glomerular filtration, drugs that are bound to plasma protein to bound to albumin can't pass through that filtration structure. And so this mode of transport is what drugs use in order to get back or to get into the tubules. Many times the carriers have a stronger affinity for the drugs than the plasma proteins, which enables the transfer of the drugs from the plasma proteins to the tubules, which are then excreted in urine. Okay? And there are two types of carriers, both of which are relatively non-selective and bind to a wide range of drugs. We refer to the first type as organic cation transporters, OCTs. These transporters bind to cations, meaning they interact with drugs that carry a positive charge, which are typically organic bases. And then the second type, organic anion transporters. So these transporters bind to, you guessed it, anions, meaning they interact with drugs that carry a negative charge, which are generally acidic drugs as well as endogenous acids such as uric acid. These carriers can transport drug molecules against an electrochemical gradient, so they can reduce the plasma concentration nearly to zero. Another connection between metabolism and renal excretion involves specific carriers that are important for secreting drugs into the tubules. These carriers also play a role in transporting metabolites into the kidney tubules. So this is particularly important for glucuronide and sulfate conjugates, okay? And so as you can see here, metabolism serves two purposes. The first goal is to increase the drug's water solubility, enabling its retention in urine, because we want the drugs to stay put in urine so that we can excrete it. And the second goal is to selectively transport this conjugate into the kidney tubules, okay? So this process shows how metabolism facilitates drug excretion and elimination through the kidneys. Beautiful. And this leads us to the possibility of drug interactions. So drug interactions are possible due to the non-selective nature of carriers, which can bind to multiple drugs. When a patient takes two drugs that rely on the same carrier for transport and excretion into urine, the carrier may have a higher affinity for one drug than the other. It may like one drug better than the other, right? So this preferential binding prevents the less preferred drug from being excreted. So for example, if we have a patient here that takes aspirin, this can inhibit the excretion of penicillin into the urine, okay? So what happens then? We said there would be a decrease in excretion due to the presence of a tubular secretion inhibitor. That means that the half-life will be increased, so penicillin will be less excreted, so it will remain longer in the body. So the half-life will be increased and you will have a longer therapeutic activity. But we have a problem here because it can lead to potentially toxic effects if the concentration of penicillin becomes too high. Prolonged exposure to high concentrations of an antibiotic such as penicillin may also contribute to the development of antibiotic resistance. Okay, so that just shows how drug interaction works, okay? But that's secretion. That's the process of tubular secretion. We're moving drugs from the bloodstream directly into the tubules using specialized carriers, okay? Let's move on and explore in more details the factors that influence renal drug excretion. If you recall back into the drug absorption lecture, we covered the ionization state, which refers to whether a molecule exists in a charged or uncharged form, and it influences its solubility and permeability. Now, we also talked about how there are different pH values in the body, and some drugs are more or less lipid soluble as a function of pH. This is because they have different ionization sites. Depending on the pH, some drugs can either be charged or uncharged. Okay, let's break this down. Let's consider two compartments in the body with very different pH levels. The compartment here on the left has an acidic pH, while the one on the right has a basic pH. So looking at this, if the pH levels differ between two compartments, what happens to the concentration of the drug anion in each one? Let's break this down. The symbol for the drug anion is A-, okay? In the acidic compartment, the dominant form will be the protonated form, AH, due to the low pH. AH is neutral, doesn't have a charge, so it will easily cross cell membranes. It will cross lipid membranes more easily. The majority of the drug in its uncharged form will cross the membrane into the compartment. What happens then? Once the AH form, this neutral form, is in the basic compartment, the pH favors the charged form, causing the drug to deprotonate into the A- form. So now we have a negative charge. This pH differences increases the passive diffusion of the drug through the membrane, increasing its concentration in the basic compartment. Now, the drug's ionization causes this phenomenon called the ion trapping effect, which concentrates the drug in the basic compartment if the drug is a weak acid. Okay? Let's apply this to something. Let's apply this concept, the ion trapping effect, to the elimination of aspirin so that we get the bigger picture of how this all works. So urine pH can vary between 3 and 8, depending on factors like diet. So let's first describe how aspirin ionization affects its solubility and ability to cross cell membranes in acidic versus basic urine. So we're applying the concept that we just talked about. And second, let's determine which substance would enhance the aspirin elimination. Second, let's determine which substance would enhance aspirin elimination through the kidneys. We have sodium bicarbonate, which is a base, and also orange juice, an acid. In acidic urine, more aspirin will be in its uncharged protonated form, making it neutral. Okay? However, in basic urine, more aspirin will be in its charged form, A- form, this negative charge here. The charged form has a lower capacity to cross cell membranes, meaning it gets trapped in the urine. This happens because the blood's pH here is lower than the urine's pH, creating an ion trapping effect. Okay, we're trapping the ion. This happens because the blood's pH is lower than the urine's pH, creating an ion trapping effect. We're trapping the ion here. Okay? And the other thing is that the charged form is more water soluble, increasing aspirin's solubility in basic urine, okay? So to increase the concentration of aspirin in the urine and promote its elimination, we should administer a base. Between sodium bicarbonate and orange juice, sodium bicarbonate is the base that will make the urine more basic, increasing aspirin elimination. Interestingly, sodium bicarbonate is used in treating aspirin overdoses because it promotes the drug's elimination from the body. Okay? We've covered a lot in this lecture, but let's now move on to another process of drug excretion, biliary excretion. Okay? Biliary excretion involves the elimination of drugs through bile. and is closely linked to enterohepatic circulation, which is a circulation between the gut, entero, and the liver, hepatic. Okay? Hepatocytes actively secrete drug molecules into the bile, which then carries the drug to the gut for excretion. So let's break this diagram down to better understand the relationship between biliary excretion and enterohepatic circulation. In the liver, metabolism occurs, okay, and liver cells can transfer various substances, including drugs, from the plasma to the bile. Bile not only aids in digestion, but also serves a route for excretion of various substances, including drugs and their metabolites. Specific transporters such as organic cation transporters, organic anion transporters, and P-glycoproteins facilitate this transfer. What bile does is effectively transports various hydrophilic drug conjugates, particularly glucuronide, into the intestines. Once the conjugates reach the intestines, they undergo hydrolysis, returning to their original drug form through the intestinal microbes' enzymatic action. So now the drug has returned to its original form, and it can eventually be reabsorbed through the gut walls and get back into the bloodstream. This is what we call enterohepatic circulation. So this involves the transport of conjugates through bile into the intestines, the hydrolysis of these conjugates in the intestines by enzymes secreted by microbes, and drug reabsorption. For certain medications, this process creates a reservoir of recirculating drugs, accounting for up to 20% of the total drugs in the body, which prolongs their efficacy. Okay, so bile excretion and hepatic metabolism effectively eliminate several drugs, forming conjugates that carries transport into bile and then into the intestine. For example, the enterohepatic circulation recycles morphine and estrogens through the bile and intestines, hydrolyzes the conjugate in the intestine, and reabsorbs it, creating a drug reservoir. Okay? The microbes in the intestines play a very important role in this process by secreting enzymes that hydrolyze the conjugates. Now, what can happen if we take some antibiotics then? And these antibiotics are going to affect those microbes. They're going to kill part of those microbes. So that implies that we will impede the intestine's reabsorption process, potentially leading to an increase in drug excretion. Increasing excretion will lower the plasma concentration, potentially decreasing the drug's activity or shortening its half-life in the body. That's biliary excretion. Let's now move on to systemic clearance, which is an important parameter here. The definition of systemic clearance, so clearance by the whole body, is a volume per unit of time. It's the volume of plasma or blood that is cleared of drugs per unit time. There are different types of clearances, including renal clearance, kidneys, hepatic clearance, liver, and total body clearance, which is the sum of all clearance pathways, all clearances. So it describes the ability of the whole body to eliminate a drug. And so we can write the systemic clearance, the clearance by the whole body, is equal to the hepatic clearance plus the renal clearance plus the clearance by other organs. The notation for clearances is CL, and its unit is a volume per time, so liters per hour. And it's related to the amount of drug cleared per unit time, which we call the rate of elimination. The rate of elimination is the amount of drug eliminated from the body per unit time. We express the rate of elimination in milligrams of drug eliminated per hour. The following equation right here will relate clearance to the rate of elimination. Okay, so the rate of elimination in milligrams per hour is equal to the clearance in liters per hour multiplied by the plasma concentration of the drug in milligrams per liter. Okay, so the clearance accounts for all the processes in the body that are going to eliminate the drug. Let's take a closer look at the hepatic clearance. This parameter describes how the liver eliminates a drug. So let's say we have a drug with a hepatic clearance of 30 liters per hour, and consider that the liver's blood flow is around 90 liters per hour. So then what does it mean for a blood flow to have such a high hepatic clearance? Well, then this suggests that the liver will clear or eliminate 1/3 of the drug in one blood passage, either by metabolizing it or secreting it into bile. So this means that liver blood flow will influence clearance, okay? So the more blood flow through the liver, will influence clearance. It will influence the elimination of that drug. Now we can define another parameter, which we call the hepatic extraction ratio. It's a measure of the liver's ability to remove a drug from the blood during a single pass through the liver. And this parameter is to relate the hepatic clearance to the hepatic blood flow by a simple relationship, which is that the hepatic clearance is equal to the hepatic extraction ratio multiplied by the blood flow through the liver. So the hepatic extraction ratio ranges from 0 and 1. You also have the option to express it as a percentage. So for a hepatic extraction ratio of 1, the liver clears all the drug in a single pass. One pass of blood flow through the liver eliminates all the drug. That's the maximum elimination by the liver. A hepatic extraction ratio of 0 indicates that the liver does not clear the drug at all. It's a drug that's not metabolized or excreted through bile. So an extraction ratio close to 1 indicates that the liver efficiently removes most of the drug, while an extraction ratio close to 0 indicates poor extraction by the liver. Okay? Another parameter is hepatic bioavailability and the hepatic extraction ratio in this context. So remember this diagram we used to explain bioavailability? Well, we can also express liver bioavailability. We can see a correlation between the bioavailability and the hepatic extraction ratio. The hepatic bioavailability is 0.25 or 25%. That means that only 25% of the drug that enters the liver will leave the liver and reach the systemic circulation. So if you have 80 milligrams of drug going to the liver, only 25% of it will get to the systemic circulation, which is 20 milligrams. This implies that the liver eliminates 75% of the drug. That means we have a hepatic extraction ratio of 75% or 0.75. Okay, so a drug with a lower hepatic clearance is one that the liver does not effectively eliminate. It's unlikely to have been metabolized or excreted through bile. But drugs with high hepatic clearance will have a high hepatic extraction ratio and will be very well metabolized by the liver or excreted through bile. And we can try to have a look at the hepatic extraction ratio and classify the drugs. But generally, we say that drugs with a low hepatic clearance have a clearance under 20 liters per hour or a hepatic extraction ratio under 20%. Example of drugs with low hepatic clearance include diazepam, ibuprofen, and warfarin. Okay. Next, we also have intermediate hepatic clearance, which is between 20% or 70%. This includes caffeine, fluoxetine, and paracetamol. And over 70%, we consider that it's a drug with a high hepatic clearance or a drug with a high hepatic extraction ratio. This includes lignocaine, morphine, and propanol. All right? Now, for the last part of this lecture, we're going to apply this concept to an exercise, okay? Let's answer some questions. So consider a hepatic blood flow of 90 liters per hour, and let's take drug A, which has a hepatic extraction ratio of 0.8 or 80%. What we're going to do is we're going to try and calculate this drug's hepatic clearance and bioavailability, okay? And if this drug is totally absorbed, can we tell if it's low, intermediate, or high hepatic clearance? So then how do we calculate this? Let's go through it. The hepatic extraction ratio is 0.8 or 80%. To calculate hepatic clearance, we are going to multiply the blood flow through the liver by the hepatic extraction ratio. So we would get a hepatic clearance of 72 liters per hour. And then to calculate the bioavailability, we said it was related to the hepatic extraction ratio. If we have a hepatic extraction ratio of 80%, that means that only 20% of the drug is going to go through. Okay, so we're going to have a hepatic bioavailability of 0.2 or 20. And that's quite a high hepatic clearance, which means not much drug goes through the liver and it has a high hepatic extraction ratio. Okay, now let's say we administer a second drug, drug B, alongside the first one. Now we're going to be looking at drug interactions here. Okay, we're going to see what happens to drug A if we administer either a liver enzyme inducer or an inhibitor. First, let's say drug B is a liver enzyme inducer. Remember what enzyme inducers are from the drug metabolism lecture. Inducers are drugs or substances that stimulate the body to produce more enzymes. Induces the body to produce more enzymes. So we're going to secrete more enzymes, which means there's going to be changes in the liver's metabolic capacity. Because what happens if we're secreting more enzymes? That means that drug A is going to be metabolized more, all right? So what's going to happen to the hepatic extraction ratio? It's going to increase. And so if our hepatic extraction ratio is 0.9, what will drug A's hepatic clearance and bioavailability be? We get a hepatic clearance of 81 liters per hour, which is higher than normal due to an increase in enzyme levels, resulting in a 10% reduction in bioavailability. Okay, why? Because we produced more enzymes, which is going to interact and change the metabolic capacity of drug A. Okay, now what if it were the opposite case and drug B was a liver enzyme inhibitor? Remember what enzyme inhibitors are. They block or slow down enzyme action on drugs or molecules. So then what's going to happen to the hepatic extraction ratio? It's going to decrease because there's going to be a reduction in enzymes produced by the liver. And how would this affect drug A? Well, we have a hepatic extraction ratio of 0.5. So our hepatic clearance will be 45 liters per hour, which is much lower, but it makes sense, right? Because we reduced the levels of enzymes produced by the liver, so we blocked or slowed down the enzyme's activity, so there is less metabolism, which means that there will be higher bioavailability. And in this case, that will be 50%. Thank you for watching this video. Make sure you subscribe to EKG Science so you don't miss a single lecture. And remember, subtract complexity and slow down. To study the next lecture, simply click the next video or you can view the entire playlist.